actually shelling this part and then adding additional lightweighting. Then we're actually verifying that design, and we're passing that design right to manufacturer, right in this case to a 3D metal printer. We're actually fabricating those parts. I'm going to talk a little bit about some of the processes here and how we can tie these things to some of the goals you're achieving in the aerospace community. Just, before we get into that, just a little bit of background. We have been a company for about 5 years now. Previously in 2017, we introduced a product called Element, and that was specifically focused on latticing and infilling of parts. And with some investment over the next 2 years from that initial release, we actually launched NTop platform, and we took all the lessons learned that we applied to lattices and actually rolled those into even more geometry capability. And then ultimately in 2020, this first quarter, we released, after our launch last year, released toolkits. And the idea is that we have an interface that allows you to prepackage workflows. And we've done some of those for our most common use cases and for our customers. So we'll talk a little bit about. One of the biggest things when we talk about software though, and when we're showing some of the shapes and geometries that we can do in our software, it's really important for us to be able to actually demonstrate that these can actually make it from outside of the computer and into reality, right? And so we've worked with hardware partners across the country and across the world to like fabricate these parts, either by laser powder bed fusion or E-beam or plastic and polymers, SLA. Really no limitation in terms of manufacturing method. Really, it's just limited to the engineer designing for the process that they're going to fabricate. So there's a few examples, and we'll cover a couple of these here. When we talk about our software, we actually talk about, and what is advanced geometry? And ultimately, advanced geometry in our scenario is that we're actually taking geometry and representing that as an implicit modeling equation. And when you can model geometry as an equation, it really unlocks the power for advanced design. And the biggest difference from other data types is that we really don't represent data as discrete parts or boundary representations of data when you think of traditional CAD surfaces, or if you think about a surface mesh from an STL, a combination of triangles that form the outer geometry of your part. And when you think about other things, when you think about volumetric mesh and simulation, those are volumetric tetrahedrals, or it could just be point data. And so the key is that we can wrap all of these geometry types with our implicit math equation. And then as we do that, we use these the concept of sign distance functions. And in this case, we can use these sign distance functions to visualize in this scenario a distance field. And that allows us to manipulate geometry in ways that were previously impossible. And we'll talk a little bit more about that. So in terms of lightweighting, there's we've kind of hovered around 3 parts that are most easily enabled in our software. The first one is a shell and fill. And so the concept there is with additive manufacturing, or really any advanced manufacturing process, you're only identifying the walls of the structure to support whatever the load is, right? And then if you think about aviation and monocoque structures, you basically have a stressed skin that carries most of the load, and that load is passed through the part as needed. And so in that pass-through part is where we consider a fill, right? And that could be a lattice, that could be some sort of periodic structure, a number of different things. In terms of lightweighting, there's an algorithmic approach where you can use topology optimization, and you can look at the load path and help visualize your load path to identify where material needs to be. And thirdly, we're going to talk about one called field-driven design, and that kind of ties in most closely with our implicit modeling technology. When we're done, hopefully we have some questions and I can answer those for you. So previously we talked about our software platform and having packaged workflows. And the idea is that we've taken some of these techniques and approach, whether it's architected materials, where we're actually custom tailoring periodic geometry, whether we're just lightweighting, whether it's topology optimization, or using advanced additive manufacturing, or even the FEA. We're using all of these prepackaged workflows to kind of help make our users more proficient. Right? And so an example of that would be a hydraulic manifold, right? And then the idea is that you have some sort of design space, And then you ultimately want to lightweight that design and design for the process. In this case, we used a shell and fill type approach. And we used 3 different toolboxes from our software to do that. First, we used architected materials, and then we used lightweighting, and then we did some design analysis to validate those performance of those parts. And so, there's many latticing tools available today, but we're a class leader in that we allow you to not just use a uniform lattice, but actually kind of to tailor that lattice or a periodic structure for what you need. So in this scenario, we did a relatively not very dense lattice in this case, and we shelled the actual part inside, and we preserved all of the hydraulic passageways. And as part of this, we actually used, we did an FEA simulation of pressure on those pathways, and we used that to make sure that we kept a minimum wall thickness that could sustain the pressure load in this scenario. And so in this case, we can also use that pressure load data to vary the lattice so that the lattice actually gets dense or even a solid material near those passages. And you can kind of see this in this variable lattice in the upper right-hand corner. We did a similar approach with a uniform gyroid. And depending on the type of response or the loading conditions, you may want a stiffer structure like a gyroid compared to a beam-based lattice. And so you can notice that in these 2 approaches, that we were able to get similar mass reduction, in this case 77%. And then ultimately, we can actually tailor the geometry. In this case, we went with a larger unit cell in the gyroid, but also enhance the thickness near those passageways. So these are all things that are relatively trivial to do in our software. Along those lines, for this manifold, we actually took a topology optimization approach. And this is another technique to remove material where it's not needed. In this scenario, we designed for a additive printing setup. So we minimized material or specifically unsupported material in this scenario, and basically only thickened the walls where we needed them and preserved the outer interfaces where you would have hoses or other clamps mount to the manifold. You can kind of see here, we use a traditional SIMP-based approach. In this case, we optimize for compliance, so the highest, stiffest structure. And in our software, video is a little granular here, but we actually show the FEA elements and then how those are being used to like erode away material until we reach the volume fraction that we're targeting. So just a little closer view here now of that hydraulic manifold and how we're actually able to capture some of that geometry. Interesting approach here in the second iteration, we actually use, we actually change the part in terms of the build direction. In this case, we're looking probably some laser powder bed fusion type scenario. And we said, hey, we want to vertically orient this part rather than just mounting it. And what would that scenario look like? And you can see that's relatively easy to achieve in our software. One thing I do want to highlight, and I might go back a couple of slides here, is that you'll notice this faceted geometry associated with the topology optimization. We can actually handle all of that smoothing inside of our software. Just in our scenario, it's a simple function or a block that applies that smoothing and repairs that surface from the topology optimized part. And we actually bring in the critical interfaces where we preserve the primitive shapes of, that are necessary to thread and mount the flanges on this part. So in that scenario, we covered both shell and infill, and then we also covered topology optimization. And we'll talk about those in future concepts here. But the other piece is that we're going to talk a little bit about fields. And fields, are, if you didn't know it, they're all around us. So you, usually as engineers, you think of parts and you think of a stress field, or maybe you think if you're a fluid dynamicist, you might think about a fluid field, right? Or you might think about a thermal field and heat emitting from something. So those fields not only surround the physical part itself, but also the space around that, especially for like a fluid, where you can actually have a combination of a fluid field. You would have a thermal field associated with the part and the fluid, and you can have potentially stress and other things related to those. So the idea or concept here is that we have a bar in different loading conditions, or excuse me, a beam. And in this scenario, we're using a stress analysis to look and modify our geometry, in this case, an infill for lightweighting, but we're going to selectively vary the thickness of this lattice so that at areas of high stress, we actually have more material. This goes back to the concept of lightweighting. It's just putting material where you need it and removing it where you don't. So to do this, we have a concept called the ramp. I'm not going to spend too much time on this, but the idea is that you can have an object. In this case, we have a sphere modifying a lattice, and we can actually use, in this scenario, a conversion from a distance away from an object to thicken the lattice. In this case, on the right-hand side, the further you get away from the sphere, the denser the lattice is going to get. And that's all this is a transfer function that allows us to relate a distance field to an actual engineering value. So that might be a stress, and we need to convert that into a beam thickness, and that's why we're doing this here. So along those lines, a combination of things is we worked with a customer called Cobra Aero, and they're in the business of designing and printing engines for drones. And in this scenario, they actually wanted to print this intake manifold, and then they wanted to be able to optimize it both for manufacturing, but also for performance, right? And so in this scenario, they wanted to fill this internal chamber with a lattice, and they wanted to vary that lattice based off a flow and a thermal field. And so we were actually able to combine these two fields together and using the block system on the left, tailor this geometry in this lattice so that they got the flow conditions that they wanted. And this is a very successful project, and we have some videos and other things on our website if you'd like to learn more about that. Another one, this is more of a generic approach that's not algorithmic, but the idea is the use of a concept of a CubeSat, and then being able to make a digitally modular design and be able to print and manufacture that in a much tighter time frame than could be done by just ordering commercial off-the-shelf hardware. And so it looks like I need to update this slide. So NTop was installed, and this part was actually flight qualified within just under a week. It was fabricated in 2.5 days. The previous part actually had a 6 to 10 week delivery time. So in this case, we were able to make a digitally modular design. On the left, we made an aluminum CubeSat bus, and on the right, we actually used an Inconel one, or Inconel material to produce this other CubeSat bus. And the idea was that with Inconel, you can achieve a much finer weld path than you can with aluminum, and therefore you're actually able to make, even though you're using a denser material, ultimately allowed to make a lighter weight structure. And in this scenario, we can actually, whoops, not going to touch my mouse there. We can actually apply that infill to this part and make really thin walls. So in that scenario, we not only reduce weight, but we also reduce stiffness, and then we had a much tighter turnaround time on that part. Previously we talked about topology optimization, and this is actually a great example of that. It's a notional satellite bracket. The idea was to use topology optimization to minimize material just where we need it. So this scenario, this bracket has loading at the two ends and a cantilever type load. And so we're able to actually remove quite a bit of material from this part. And in this scenario, we actually just left the beams that were there as solid parts, right? So there's no infill, no shelling being applied to this. We'll talk about another scenario where we can actually enhance a top op solution like this with the other techniques that we've talked about previously. It's just a nice example of that part. So showing the slide again, because I want to show, again, we're kind of re-emphasizing some of the process here in topology optimization, but also the use of these fields. And it's going to come up in this next example. And so the idea is that a topology optimization produces kind of this rough part at the end of the day. And then nTopology is actually able to allow to smooth that part, we talked about previously. And then we're actually able to bring back or boolean back our parts back into one final piece that are critical interfaces. We're able to do this all in one piece. If we were to take that a step further, the idea is that we could use this automotive type bracket that was done for topology optimization. And what we did is after the solid topology optimization was performed, we actually did another stress analysis on that part. And then the result of that stress analysis is on the right. And this is that concept of that stress field. And what we wanted to do is we actually shell this part. And through the use of these fields, we can actually variably shell parts. So you don't actually have to have a uniform wall thickness over the entire part. In this case, we can actually vary that part. And what we've done is that where there's areas of high stress, you're going to get a near solid wall thickness. And then areas in blue or low stress are actually going to be a thin wall. And so you can see how this part actually is variably shelled. And so we went from an initial mass reduction of 80% with the topology optimization, and we're actually able to shave another 8% of the weight off of that part based on the original design volume. And then more succinctly is that the original top op, from the original top op, that was a solid part, and that shelling, we were able to cut weight 24% from those two pieces there. So really able to cut weight. And finally, I wanted to leave you with you not always have to design your parts for mass, but what if you actually want to design them for both performance as well? In this scenario, we actually used a periodic gyroid to produce a heat exchanger. What's nice about gyroid structures is they have both an interior domain and an external domain that are isolated from each other. And in this scenario, we partnered with HRL to print this in their 7000 series aluminum. And so we were able to increase the surface area of the part by 150%. And then by using this 7000 series aluminum, we're actually able to use a thinner wall than we could use with an LC10MG, like Cascade aluminum that's common in additive manufacturing. And so we were able to get even higher performance based on minimizing the wall thickness and increasing the surface area. And those two things matter most to geometry. And I think the key here is that with this geometry, and although very complex, you can still do your traditional CFD and other static analysis to those parts to ensure that you're going to get the performance that you need. Right? And in this scenario, we actually used an iterative design in the sense that we produced the design on the left. In this case, it wasn't very printer friendly for additive manufacturing. And then we ran some CFD on that and noticed that we had some stagnation in the bottom of this part. And so when we redesigned that, we tried to divert the flow and make it perform, or that flow to flow more axially within the part. And we're actually able to increase the heat transfer coefficient overall of that part. And so ended up being really successful at being able to take some lessons learned from that CFD analysis and apply them back to the actual part. And again, here with this oil cooler, you can see the isolated domains. In this one side, we have a hot side and we have a cold side. And that's all I have for today. If you have any questions, I'd be happy to stay on and see how things go.
Thank you. I think we do have quite a few questions in the Q&A. So to start out, the first one is, for your shell and fill techniques, is there integrated considerations in the software for powder removal, for LPBF, and the effect of the holes that would be needed on the part properties? Yeah, so I think in this scenario, I think there's a big push for everything to be algorithmic today and kind of be a one-press button and black box. And in nTopololgy, actually our company founder named the company because he really wanted to enable any geometry, and not to have engineers be bound by a particular or limited by their tools. Right, so in that scenario, we're doing these shell and fill techniques, but we don't replace the engineer in that. But if you need to add perforations for additive manufacturing or whatever design processes, we can add those quite easily. And so, but we don't have a magic button that replaces that design engineer to make some of those design and manufacturing process decisions. So, awesome, thank you. Another question from George. Are you using actual performance of additively manufactured lattice in your load calculations? Yeah, so in terms of lattices, we make it really easy to draw lattices, and we make it easy to analyze them. But some of those things, I'm a big background in FEA, and so I'm always going to say that a simulation is great, but it always needs to be experimentally validated. And so in those scenarios, we can help you make design decisions on what might be the most stiff, or what might be the stiffest lattice or the best performing lattice for that particular design. But ultimately, even though we're going to simulate and provide more insight, and we can actually allow you to vary apart or thicken lattice where you need to,
ultimately, we're not going to replace that experimental piece. It's still software and still needs to be validated. So, yep.
Thank you. A question from Duncan. Hi, Ryan. Really like the NTop software. Is there functionality for increasing dimensions based on the type of material removal surface finishing to be used?
Yeah, so I think in that scenario, and then this kind of goes back a little bit to the modeling and experimentation side, if you know, or if you have a process where maybe maybe there's a scenario in some of these parts where you need to have, where you need to have extra material, we can add those offsets and blends as needed. And then, but again, we're still going to rely on the process or the design engineer to make sure they build those into their part. Yep. So.
Awesome. And we'll end on one more question before we get started in our virtual networking session. From Pranav, does NTopololgy software consider optimum support structure while topology optimization for different AM processes?
Yeah, so I keep relying on the design engineer, right? And the key is just to unlock geometry and allow the engineer to do those. In terms of lattices and periodic structures, those are great for support structures, and we certainly allow the generation of supports to be done within our software. And that's also an active area of development for us so that we can improve that to help make that even easier. So, yeah.
Awesome. Well, thank you so much, Ryan, for joining us today. We will now begin our virtual networking session. Our next presentation will be at 2:30 p.m. Pacific time from Additive America. Thank you.
Thank you. Take care.
You too.